All right, and today we have lecture 7 in chapter 3 on ideal gases. So we're essentially going to learn to use the thermodynamic properties of ideal gases. Well, what we saw at the end of last lecture is that there were two particularly relatively easier systems, part of the system. You had the incompressible fluid that was here, and we went through the equations of state for the incompressible fluid. And the other one now is when we go to very high temperatures and reasonably low pressures, which is what's going to happen at the ideal gases. And that is going to be this particular lecture. So it's out here, far from the vapor dome toward the high temperature end. So there are several ways to describe your ideal gas. Your macroscopic thermodynamic behavior is purely experimental. We're going to look at gases out here. We measure then pressure, volume, and temperature of such gases, and we can plot pressure times specific volume over temperature as a function of pressure. And for various gases, we obtain these straight lines which, for all gases, seem to extrapolate to one and the same value. This value is R bar. This value, in limiting case for zero pressure, is 8.3 kilojoules per kilomole per Kelvin. The same for all gases. So you can express that in kilojoules per kilomole per Kelvin, in BTU per pound mole per Rankine, or in pound foot per pound mole per Rankine. It's all expressions of energy per kilomole per mole per Kelvin. That is the universal gas constant. Now, there is an interpretation in microscopic thermodynamics, which I personally find easier to understand. The definition of the ideal gas, then, is a gas of particles, any particles that don't interact with each other. And then there is a relation between the ideal gas constant, which is the macroscopic, essentially chemistry-based value we gave a minute ago, and a microscopic thermodynamic property, which is the Boltzmann constant. That relation is that your ideal gas constant per mole is Avogadro's number times this Boltzmann constant. So these two constants are related by the number of molecules per mole. In other words, the ideal gas constant, which is per mole, expresses the exact same thing as the Boltzmann constant per particle. All right, so once we have the ideal gas constant, we can then write this previous expression as P times V bar, so specific volume per mole, is R bar, the ideal gas constant, times temperature. Well, we know that the specific volume per mole divided by the molecular weight is the specific volume per mass, per kilogram. So that means we can do exactly the same operation on the ideal gas constant and define a ideal gas pseudo constant, which varies from gas to gas because it's ideal gas constant divided by the molecular weight. So this is still constant within the same gas, but it is dependent on the gas. And you can write your PV as RT as PV is RT without the bars, and now you have it per mass. If you express this as a function of the total volume of your system, your PV would be the mass of your system times RT. If you express the total volume as a function of the specific volume per mole, you have the well-known rule, PV is nRT, but this in our notation would be R bar T. Okay, all these expressions tell you that if you're going to go in a PV diagram, you have a hyperbola, because the product PV is a constant, and so P is 1 over V. P is N R by T over V. So this hyperbola would look like this for 1T1, for T2, for T3, looks like this. These are the isotherms. That is the equations of state for the ideal gas expressed in a variety of ways. All right, we need to explore what the limits are of this ideal gas model. Where can you apply it? Well, so you know that it works out here at very high temperatures and lower pressures. But if you get closer and closer to the vapor dome, you know that it somehow is going to break down. Where? Well, one defines the deviation from the ideal gas by this quantity Z, which is called the compressibility factor. So it's basically P V bar over R by T, which would be 1 for the ideal gas, but it deviates from 1 here. So we can plot that compressibility factor here as a function of the pressure. And of course, in the limit of low pressure, that converges onto 1. This is the ideal gas right here. But experimentally, you see that while at high T you have small deviations here from the ideal gas, at lower temperatures, you can have quite dramatic deviations from the ideal gas, maybe a factor of 2 or 3 here. You can express the same quantity, the compressibility factor, per mole, like we do here, or per mass, like we do here. But it's the same concept. In fact, it is so much the same concept that you can create a universal set of curves for all gases in this case. Again, that is the macroscopic expression. There's a microscopic expression which might be easier to understand. You can see that as you go to lower temperatures and to higher pressures, you're pushing the molecules or the particles that you're studying closer and closer to each other. As you decrease the distance between the particles, you necessarily must increase the interactions between molecules, and we define the ideal gas as a gas of particles that don't interact. So it's the same reasoning as we have with this chart. This simply expresses the idea that the closer you put your particles, the more likely they are to interact. The next step is we can make this Z versus P chart really a universal chart for all gases. And the way to do that is define a reduced pressure, which is the actual pressure over a P sub C, which is a characteristic of the ideal gas, of the gas. It's tabulated in table A1. And a reduced temperature T sub C, which is also tabulated in table A1 for various gases. Then you have to define some sort of reduced specific volume, but it's really V bar, which we know, R bar, which we know, and then this T sub C over P sub C. So that's a little bit of algebra. And once you have done that, you can express this Z as a function of this reduced pressure, here, P sub I, which is this axis, for a variety of T sub I's. And these rules, these general curves, are valid for all the gases, except you have to put the parameters in for PC and TC that you'll find in table A1. Why is that useful? Because there is a practical engineering limit to where we can use the ideal gas model. And the word is you use the ideal gas model until your Z deviates by about 2%, by 2% or more from the ideal value from Z equals 1. So 98%, which is actually barely here, or 102%. And the accuracy of your calculations depend on how much you deviate from that. And so there is a question of sensitivity of the problem you're solving to accuracy. There's another concept that you may encounter in chemistry or in thermodynamics further on, that is the virial coefficients. Well, all one really does is expand this Z, the real practical Z that you see here, as a function of pressure in a series in a Taylor expansion, and the coefficients of the Taylor expansion are called the virial coefficients. They express to various degrees the number of interactions between particles, but we won't go into that. That is explained in microscopic thermodynamics, which this is not. For us, this is the important number. 2% deviations is allowed, and more than that, probably should look at another approximation for your gas. Now, let's move at what we can actually do. How does the fact that you're dealing with an ideal gas simplify the equations of your problem? So let's remind us that the equation of state is PV bar is R bar, specific volume per mole, and ideal gas constant. Or per mole, you have this, if this is the real volume, or per mass, you have that, but this R is R bar over the molecular weight. Okay, so now it can also be shown, although that's more difficult, that in the ideal gas, the internal energy is a function of temperature only. and not of temperature and pressure. Again, that's a demonstration that comes from microscopic thermodynamics. Again, I can hand wave it for you. If there are no interactions, the only thing that matters to the internal energy of the system is the vibrations of the individual particle, where the vibrations of the individual particle have nothing to do with the neighboring particle, so the pressure should in no way intervene in that equation. That is why U is U of t. Well, if U is U of t, and CV is du dt at constant volume, then CV is CV of t. So that's easy. That means that U of T2 minus U of T1 is simply the integral between 1 and 2 of CV of t dt. This integral is an equation of state, but you need to know explicitly CV of t. The good news is you at least got rid of the dependence of CV on P. That's the main result, actually, of having the hypothesis that you're dealing with an ideal gas. And then you can set yourself as 0, which in principle will be that 0 is at 0 Kelvin, although our tables don't use that, but we can use that if we want. In any case, we're going to solve for differences, T1 to T2, so this actually doesn't matter all that much. Now, the case of the enthalpy is a little bit more complicated. So the enthalpy is U plus PV, so you would at first sight think that this P comes back and that H is more a function of P than U would be. Well, but we can replace PV by RT. That's our equation of state. So that means that the P dependence actually vanished. It's a result of it being an ideal gas. So H is only an H of T. Therefore, Cp, which is dH dt, is only a Cp of T. And therefore, you can also write the enthalpy as H of T2 minus H of T1 is the integral of Cp dt. Remember, U, the change in internal energy, is integral of the specific heat at constant volume. The change in enthalpy is a function of the specific heat at constant pressure. These are two important distinctions to make. Well, now, how can we go to the specific heats? Well, so far, what I have said is that energies, so enthalpies are internal energy, and the specific heats, constant pressure or constant volume, of the ideal gas is not pressure dependent. That is the main benefit of working with the hypothesis that you have an ideal gas. And this is something I want you to remember. Ideal gas, no pressure dependence, only temperature dependence. Okay, so we take the equations we had before, and let's work a little bit at looking at the difference. I'll do it in bars and specific values per mole. Cp, specific Cp minus specific Cv, well, that's dH dt minus du dt. I remind you that these now are exact differentials because I could get rid of the concept that I had to keep the pressure of the volume constant. Now, let's take H is U plus PV minus du dt. I distribute my differentiation over this sum. So this is du plus RT over T minus du dt, and that is nothing else but R bar. This is the only one that comes here, because du dt and du dt, they cancel out because of this minus sign. So I'm left of d of R by T dt. R bar is a constant by definition, so that means R bar times dt dt, so that is simply R bar. The same can be done, and I'll let you play with the algebra, with the values per mass. Cp minus Cv is R per mass. Well, remember the definition of K. K is this ratio of Cp over Cv. So this equation comes by definition. Now, that means that if I take Cp minus Cv, that is Cv times K minus 1. I'm just getting that out of here. And we know that is R bar. We had it here. So now we have two equations and two unknowns, Cp and Cv. So we can solve for Cv and Cp. Cv is simply R bar over K minus 1, and Cp is K R bar over K minus 1. We can do exactly the same thing per unit mass. It makes no difference. So that now tells you that if you know this ratio of specific heat per constant pressure to specific heat per constant volume, you necessarily know both Cp and Cv, at least on a molar basis. If you know your molecular weight, you also know them on a mass basis, of course. So if you know your temperature difference, and if you know K, you really know everything. You can calculate du, dH, all the quantities in your problem, all the energies in your problem, not the entropy, that won't work. But all the energies in your problem can be calculated with no other knowledge needed than K. No tables, nothing, just straight out of that. Okay, so what is this K? Well, to the rescue comes, again, microscopic thermodynamics or empirical observations. Let me start with empirical observations. Take Cp measurements, renormalize to the ideal gas constant, Cp bar per R bar, and measure it for argon, neon, helium. It's all just right here, 2.5, plus or minus practically nothing. I can do this now for hydrogen or oxygen, and at least at low temperature, low pressure, it's surprisingly equal to 3.5. Okay, so what's going on? This is Cp, and so these gases are monoatomic, and it seems to look like 2.5. And these gases are diatomic, and it seems to look like 3.5. So let's just write Cp for monoatomic is 2.5, is 5 halves. Cp for a diatomic is 7 halves, 3.5. Well, there is a microscopic explanation for the exact same thing that goes back to the Boltzmann constant. If you have a monoatomic particle, so that consists really of one ball, how many degrees of freedoms do I have? In what directions can it vibrate? Well, it can vibrate up and down, it can vibrate left and right, and it can vibrate in and out of the plane of my screen. So it has 3 translational degrees of freedom. There is a theorem in microscopic thermodynamics that you can have an energy stored as internal energy in vibrations that's a half kb per degree of freedom. So that means Cv is 3.5 kb. Cv plus Cp is R bar, so that means Cp is 5 halves R bar. And there we are. That's just that. It works for diatomic gases too. Your diatomic gas has 2. Take a dumbbell model. You can have the 3 first degrees of freedom, vibrate this and or vibrate that or vibrate like that for all 2 together, rigidly together. So that's your 3 translational degrees of freedom. On top of that, the dumbbell can rotate. They can rotate in the plane vertical to the well, they can rotate like this, or they can rotate like that. That adds you 2 degrees of freedom, 2 rotational degrees of freedom. Cv is 5 halves R. Cp is 1 R more, so Cp is 7 halves R. That really bears out the experiment, and it's an intuitive explanation that's actually quite correct. You can go to more complicated molecules as the CO2 or H2O, and now you see that you get higher and higher values, but they can do all sorts of strange things. This is much more complicated. You can imagine that triatomic molecules have more degrees of freedom, and basically all we can say is that the specific heat is higher than 9 halves R here, and higher than 7 halves. So for Cv, Cp higher than 9 halves, Cv higher than 7 halves R bar. Okay. So there you probably have to measure it, but at least we have something very intuitive for monoatomic gases and diatomic gases. Let's push this whole thing a little bit further. Let's make the approximation that none of this is temperature dependent, which was the picture we had before. If we work at low enough temperature, these things are sort of constant. So if they're not temperature dependent, this is your value for your Cp and your Cv. You just know what it is. If it's a monoatomic gas, 5 halves for Cp, 3 halves for Cp. Diatomic, 7, 3. So you know everything. It's temperature independent. That means that U2 minus U1, which is that integral, is actually Cv, which you can take out of the integral, T2 minus T1. H2 minus A1 is Cp, T2 minus T1. You know everything. You can reconstruct everything as far as energies go from just knowing the temperatures and the nature of the gas, monoatomic or diatomic. All right, so this is quite practical. Let's now take a look at what happens when these things do work in a polytropic process. Now, let's be careful a little bit. To a certain extent, the ideal gas law itself is a polytropic process, but it can be generalized to this. So we had seen when we went through the class on polytropic processes that the work is P2V2 minus P1V1 over 1 minus the power law of the polytropic process here, except if that power law is 1, as is the case for the ideal gas. In the case of the ideal gas, the work then becomes P1V1 log of V2 over V1, P2V2 log of V2 over V1, and since, of course, PV is RT, P1V1 equals P2V2. So we have work that's simply a logarithmic functions of the volumes. When you expand an ideal gas in a piston system, this is the work that you're going to get. You just need to know pressure and volume at one point, and you can get the work. Essentially, your path is defined by the equation of state of the ideal gas itself. One can push that further. We can replace these V's by T's. So you know that P2 over P1 is T2 over T1 to N minus 1 over N, which comes from here. And for N is not 1, you can then express the work as the mass times the ideal gas constant per mass times T2 minus T1 over 1 minus N. And if the transformation keeps the temperature constant, that is PV is NIT is constant, you can apply this when the temperature is not constant, but when the temperature is constant, you apply this. Then you have that the work is IT instead of PV times V2 over V1. Quite simple. You don't really need to remember these all equations at all, but you can quite readily derive them, at least in this case, in case the problem asks for it. But most of the time, of course, I will let you use your book when we have equations that become that difficult. Okay, so let's now summarize what we have to do when we have a gas in a PV diagram like this, or a substance in a PV diagram like this. Okay, so if the thing is dense here, close to the saturation thing, but dense, that's where you use superheated vapor tables, A4, A9, depending on the system. You need two parameters, P and T, T and V, T and X. If you move out and you get mildly here, you can use your variable coefficients. Yeah, all right. Or you can go further and further and further out. So you can use these when Cp and Cv are functions of T only and not P, but they are still T dependent, which would be roughly the case here. Or if they're really not T dependent either, only P dependent, then you're at the extreme limit, and then you can use these super simplified equations that are here. That's sort of the use of what you can do with gases, the gas part. Of course, we have seen this, and I will actually summarize the whole chapter. If you have a number of thermodynamic properties to look up for a certain substance, generally you need two variables. For simple compressible systems, you have the region, well, you have essentially this region. You have the region where it's incompressible. You have the region where you have two phases. You have the saturation line here and here. You have the region here, which is superheated steam, and then you go farther out, and you have the ideal gas region. For the saturated systems, you really need only variable, but only intensive property, but that's not quite true. You simply know that x equals 0 here, or x equals 1 there. You just know that by definition. Two-phase systems, here you need P and T. Here you need P and T, you need two of them. Here there's a dependence, there's P and T are locked into each other, so you need something else. And so that becomes then the quality of the steam, X. If we go here, we have the case, in the incompressible systems, which is case 5, we have Cp equals Cv, and then your internal energy here is actually the same as the value at the saturation line. Your enthalpy here is the value at the saturation line. If the pressures are really high, you have to make a correction for the compressibility of the fluid, which is in fact its specific volume at the liquid saturation line, and correction for the difference in pressures. So that's the situation here. If we go now to the ideal gas, our equation of state becomes PV is nRT, or PV is nRT here. And now you have two cases. If you are closer by, you can assume that its specific heats are P independent, but not T independent. If you go far away, you have the specific heats that are both P and T independent, and then they're given by these constants, 3½ R, 5 IR, 5, 7, or more. And that's that for today. Thank you.